Hello, my name is Dalton Spivey. This is my lab report for Physics 2211 at Georgia Tech. This lab investigates the universal law of gravitation. First, I'll state the purpose of the lab, then I'll introduce the system and its surroundings. I'll then explain key concepts such as Newton's second law and gravitational force. This lab is divided into two parts. The first part focuses on estimating the mass of a black hole using a computational model. The second part focuses on predicting the motion of a spaceship near the black hole. I'll then proceed to answer some essential questions. Introduction. The first part of the lab aims to visualize gravitational force and use Newton's second law to calculate the mass of a black hole. In this part, the system in question is a star that is orbiting around the black hole, and the surrounding is a black hole itself. The second part focuses on determining the initial velocity of a spaceship launched from a nearby orbiting planet in order to get close to the black hole without crashing into it. In part two, the system in question is a spaceship, and since the orbiting planet and the black hole both exert a gravitational force on the spaceship, they make up the surroundings. The mass of the black hole was determined to be 1.42653 e to the 34 kilograms. The initial velocity of the spaceship should be about negative 0.85 e to the 7 in the x direction and 9.5 e to the 6 in the y direction in meters per second. Key concepts. The rate of change of momentum is expressed as dp dt, where this is a momentum vector. Any vector can be represented as a product of its magnitude and the unit vector. We use this fact to differentiate the momentum vector, yielding an equation with two components according to Newton's second law. The net force acting on an object is equal to the rate of the change of momentum. Hence, F net is equal to dp dt. By the equation on the left, it is apparent that these two terms are basically just a perpendicular and parallel components of dp dt. Thus, we can use this to calculate the parallel component of F net and the perpendicular component of F net as shown on the right. Since F net is equal to dp dt, the magnitude of F net is equal to the magnitude of dp dt. In part 1 of the lab, it is assumed that the only force acting on the star is a gravitational force exerted by the black hole. Hence, we can equate F net to F gravitational. We can also assume that the magnitude of F net is equal to the magnitude of the gravitational force, yielding the equation on the right. The magnitude of dp dt is equal to the magnitude of the gravitational force. We can then rearrange this equation to find the mass of the black hole. Computational model. To predict the mass of the black hole, the mass of the star was set to 2 e to the 30 kilograms. Delta T was set to 86,400. This is meant to represent all the seconds in a day. I then used X file to calculate the V initial and the V final, which are then further used to calculate initial momentum and final momentum vectors. Delta V is calculated using V final minus V initial, and delta P is the change in P final minus P initial. I then used some simple vector calculations in algebra to calculate the perpendicular and the parallel components of F net. The mass of the black hole came out to be 1.42653 e to the 34. The second part of the lab focuses on mapping the motion of a spaceship that goes as close as possible to the black hole without actually crashing into it. For this part, I used trial and error and basically played around with the x and y components of the spaceship's initial velocity. The surroundings in this case consist of the black hole itself, as well as a nearby orbiting planet from which the spaceship is launched from. Therefore, the net force acting on the spaceship is now the sum of the gravitational force exerted by the black hole in the spaceship, as well as the gravitational force exerted by the planet on the spaceship. The motion of the spaceship was mapped using position update formula and a velocity update formula given by Newton's second law. Discussion questions. What are the differences between the net force and the rate of change of momentum and the respective parallel and perpendicular components? Mathematically, there are no differences. They are equivalent. They are also seen by the formulas derived earlier. However, in this lab, the major difference is that the change of momentum can be calculated easily based on the direct observation of the object's position, velocity, and momentum. However, the net force is something that we cannot calculate without knowing the mass of the object. What if? What if we wanted the spaceship to enter an orbit around the black hole? In order to do this, we have to reduce the magnitude of the velocity so the spaceship is bound to the black hole. This allows for us to consider rounding errors, misinterpretation of values as well. I've calculated this and through trial and error found that in order to obtain a orbit, the spaceship's initial speed needed to be negative 8.25 e to the 5 in the x direction and 1 e to the 7 in the y direction meters per second. Thanks for watching.